Vipin Kumar is a Regents Professor and William Norris Chair in Computer Science at the University of Minnesota, Twin Cities. His research interests span from data mining to high-performance computing and applications in climate, ecosystems, and in healthcare. He has authored over 300 research articles and co-edited or co-authored 10 books, including 2 textbooks, Introduction to Parallel Computing and Introduction to Data Mining, both of which have multiple editions. And among many awards and honors, he is a fellow of the AAAS, of the Association for Computing Machinery, the IEEE, and the Society for Industrial and Applied Mathematics. And in 2016, he received the IEEE Computer Society Sidney Fernbach Award. We're very excited to have him as our speaker for this LEAP lecture in climate data science. Vipin is a member of the LEAP community and is leading a research project, so it's great to hear about what he's doing. The talk today is inverse modeling via knowledge-guided self-supervised learning and application in hydrology. And as you may have seen in the chat, Vipin has told us that he's willing to have questions during his talk. So you can raise your hand or type in the chat. I'll monitor those, but you could also just go ahead and jump in if you feel so moved. So Vipin, the floor is yours. Thank you for being here.
Thank you, Kellen, and everyone for being here. This talk is about some work we are doing as part of this the LEAP project, inverse modeling via knowledge-guided self-supervised learning. And the focus is, of course, on hydrology in this one, but the applications go far beyond. And just let's see. And since I'm going to be using the term knowledge-guided machine learning quite a bit, and again, the basic idea here is that you have a scientific problem that you're trying to solve. You could use them using pure physics-based model or the scientific theory-based models. You could potentially solve them using pure data science models or pure machine learning models. And then there's a new direction emerging in which you combine the strength of both of these to make sure you have more robust and more generalizable solutions that can work with less training data and give more effective results. So the question, of course, the primary problem that we're trying to deal with is a modeling of a physical system, which for many purposes can be abstracted in a form that there is a system which is being governed by its behavior is being governed by certain drivers. For example, in our case, could be weather drivers. And we are trying to observe its response, which is of interest. In the case of hydrology, it could be the stream flow or temperature of the stream. Or in case of a lake ecosystem, it could be temperature at different depths of the lake and so forth. And this the response of this system is driven by the drivers, in this case, the weather drivers. But this relationship between X, which is weather driver, and Y, which is the response, is governed by some characteristics of the system that is given different values, given the same weather characteristics, given a different value of static characteristics S, you may have different responses. So this is sort of the situation. It's a very common situation, occurs in many contexts. And oftentimes you're interested in doing a forward modeling that is given input driver X, you're trying to find the value of Y. And of course, and we know that response is driven by the static characteristics S. And oftentimes this is the traditional paradigm has been to build a physical model that tries to represent all the intricacies of the processes, underlying processes of the physical system. And then the characteristics, of course, would be sort of coded as part of parameters of that system. And then hopefully this forward model, then given X, would give you the desired value of Y. And again, a lot of times this forward model isn't doing a good job, perhaps either because you don't have the right values of the static characteristics that you need to feed into the system, or perhaps you are not able to fully represent all the relationships, all the intricacies, all the processes at the right level of details that you needed to, or some of those relationships may not even be known to you. So this is sort of how the physical modeling sort of proceed, and people know of its limitations. And increasingly, there is an interest in using machine learning to improve this forward modeling. either via emulators, in which case you trust the forward model, but you want to just make it faster. Or in some cases, you would want to improve the quality, perhaps by using the information that's available to you, plus using some observations. So there is a lot of work on using scientific knowledge-guided machine learning for forward modeling. And many people around the world sort of have spent quite a bit of time on this one. The talk today is largely focused on inverse modeling, that is, given a physical system and its input and output parameter, that is the drivers, the weather drivers, and a response system. If you were looking at hydrology, it could be a streamflow. Then you're trying to reconstruct the static characteristics of the system that govern this behavior relationship between X and YT. And this is of course a very important problem, very difficult problem, and it's also strongly related to parameterization. In the sense that if you have a physical model and if you are able to, of course, you can parameterize it in certain contexts, but if you go to a completely new situation, you have to find the value of the parameters, and their inverse modeling could be one of the possible solutions for parameterization. So traditional approach for inverse modeling could be, sort of one of the many approaches in physical modeling literature would be that you don't know the parameters of the system S, but you do know X and Y for certain observations. So you run the forward model given X and given many of the possible values of the static characteristics sort of in a grid fashion, and see which one of those values lead to an output which is close enough to what you're observing. So this is like running multiple times the forward model with different static characteristics combinations and choose the one that has the best match with the observation. It's very compute intensive. And of course, it's useful only if you assume that the F is perfect, the forward model is perfect. Now, machine learning models are increasingly being considered for solving inverse problem. Most of this work has happened in the context of images. These models tend to contain large number of parameters and are derived from limited noisy data. And again, there are all sorts of issues with them. What I'm going to talk about is a machine learning based inverse modeling approach that brings in the scientific guidance of the scientific knowledge and then uses this to solve inverse problem in this context, that you have a time varying system, the input drivers are changing over time, the output response is changing over time, and then you're trying to figure out what those characteristics are. And in some sense, this is even though I'm talking about it in the context of hydrology, the methodology is very general and is applicable to pretty much any problem in which you have temporal input and temporal output and static characteristics. So the demonstration of this methodology I'm going to do is going to be in the context of NCAR's CAMELS dataset, which is a hydrology dataset. Actually, it has many more basins than 531, but I'm using a subset of these that have been used extensively by many people in the hydrology community that are also beginning to use machine learning. So these are 531 basins, all over the country. And you can see each of them represented by a dot. Each of these basins, for each of these basins, there are about 27 characteristics. 9 of them are climate, weather related, and 8 geomorphologic features, and 10 of them are geological features. There are 5 dynamic inputs that this has, the CAMELS data set, basically precipitation and temperature and wind speed and so forth. And there's a dynamic output we are interested in, which is a stream flow. And it just happens to have data from 99 to, I guess, from 1989 to 2010, but 20 years of data, and then we'll use some of that for training and some of that for testing.
Vipin, can you define NSE? We have a question. What is NSE?
Very good. Okay. So, okay, all right. So this, you don't need to know NSE at this time, but NSE basically is a metric of performance. Oftentimes people would use root mean squared error, RMSE, as the measure of performance. That is, you are predicting something, and then you look at the difference between the errors of what you're predicting and what the actual value is. And RMSE is a standard method that's used very extensively. But in hydrology, the community tends to use the NSE, which basically says that if I knew the past behavior and if I knew the average values at each time, am I able to beat that average behavior? So it's almost like saying that in the weather prediction, am I able to do a better job than predicting better than the average weather that I would expect on a given day? So this is a sort of short summary, but it basically is just deviation from the averages as opposed to the actual deviation. And it's much more robust in many ways, and the hydrology committee uses it almost exclusively. So going back to the experimental setup, I just talked about the CAMELS data set and all the different characteristics. And in the data is available for about 20 years or so, and we're going to use out of 531 basins for many of the results I'm going to show you. The machine learning models will be built only on the first 400 of those basins randomly selected, and the results will be shown on the other 131 basins for testing. We have done many more combinations. I'm happy to answer any questions that relate to the distribution, but just to make it clear that this is the big division. And then in many of these settings, portion of the data, more recent part of the data is being used for training to build a model, and the older part of the data is being used for testing. So basically, this is again just to make sure that the statistical model that you're building do not get overtrained on the data that you're working with. And again, there'll be some variations of this setup that you will see in the next few slides. Actually, on this one. So this is sort of a more general slide, which sort of has many different scenarios that may be of interest to people in different contexts. And inverse modeling actually is relevant potentially to all of these contexts, but lot more of these results would be for the third one. So the first context is in which you are in a gauged basin scenario. In the case of hydrology, the idea is that you have a certain number of basins, you have past history on what the weather is and what the stream flow is for many years, and plenty of years, let's assume. And the idea is that in this gauge basin scenario, given that you have a lot of data from the past, you can use it to calibrate your physical models or potentially build machine learning models. And once you build them, then you can, or calibrate the physical model, you can test them. So you can see the graphic on the right side, a variation of the picture I showed you earlier. And you can see a training in the training basins, and you can test it on the same basin, but in future years. So this is the gauge basin scenario. And in the case of physical model, that means you can do the calibration in years for which you have the observations, and then better calibration would have hopefully give you a better forward model in the test years. In this case, the past years, but normally it will be the future years. Now, one could build a machine learning model, and increasingly over the last 5 years in hydrology, many groups around the country are beginning to use machine learning models. And of course, you can build machine learning models in many different ways. And one of them would be that you build a machine learning model for each basin separately, which will be called a local model. They don't tend to do very well. But what the machine learning model allows us to do is also build a model of a collection of basins. So for example, if I have 400 basins, I can build a single model that can collectively use data from all of the basins. And as a result, it becomes a global model. And of course, to make sure that it's learning the behavior of different basins, it would need to have some characteristics. So basically in the machine learning community or the people, I guess this is the community called HydroML, the community, which is sort of the intersection of hydrology and machine learning. And these people, this community has built a series of models in which the characteristics of the basins are known. And then as a result, you can build a global model. So that means in the middle column of this, or the left column of the ML model group. And you can build a global model with known characteristics. And there are a series of papers, but the two most influential ones are by this group at Google, Kresser et al., where they showed that in this gauge basin scenario, this global machine learning model that incorporates characteristics in the global model is able to beat the best known, the many of the best known physical models that have been individually calibrated for each basin separately. And it's a pretty dramatic result. And then again, the power here, machine learning is bringing a power here simply because when you're calibrating a physical model, you're only calibrating it one basin at a time. And whereas if you're building a machine learning model, you're collectively using data from all of this model. And physical model, if it has some deficiencies, there's a possibility that machine learning model is not limited by those deficiencies. So this result is actually very powerful and very useful. And I guess it was used. It sort of allowed it sort of made the hydrology community pay more attention to the machine learning. Now, more recently, just in the gauge basin scenario, we showed that even if you do not know the characteristics, and even if you assign them randomly, and this is just a paper our group published just in WRR just a few months ago, that you can still build a global model by assigning them random characteristics, or in machine learning, as they call them, one-hot vectors. And these models are able to learn just as good forward models as one could do using the best known characteristics. Now, there's another situation, which is number 2, which is
Vipin,
yes, hello.
Sorry to interrupt, but I wonder, could you clarify the difference between characteristics known and characteristics unknown? Because I think I don't have that totally clear.
Very, very, very good question. And I really appreciate questions being asked in the middle, because this is especially this one is a very important part. So if you recall, let me. So if you go back to this data set, the CAMELS data set, 531 basins, and it has 27 steady characteristics, and the characteristics are like the elevation of this catchment, or the slope of this catchment, or the soil characteristic, how sandy the soil may be, what may be the composition of soil, what may be the porosity of the soil. So there are lots of different features that somebody may know about, and if you knew those features, you would know that if the soil was clay versus soil was sandy, hydrology will tell you that same amount of rain would have a different impact on the stream flow. Or if there are a lot of trees in a basin, the crops being planted versus the area is completely barren, the rainflow response would be different. You know, if the trees are planted, then perhaps a lot of rain would be absorbed by the soil and then evaporate. Some of the water would evaporate. But in the case of impervious soil, the water would sort of just run off. So there are all sorts of characteristics of these basins that determine the input-output behavior. And in many contexts, people know what these characteristics are. Actually, there is a project called Hydro Atlas, which has basically created these characteristics for basins, the river catchments around the world. Dave Lawrence has a question, and I would rather have him ask it by unmuting, if you could, please.
Yeah, sure. It's just kind of extending that. I think I know the answer, but I want to hear you say it. As you're putting climate as a static characteristic, which of course we don't think of climate as a static characteristic in most frameworks. So do you want to expand on why you're including that in the static?
Got it. And again, these characteristics are coming out of CAMELS, and the climate characteristics are like the average climate, in the sense that what is the average temperature, what may be the average precipitation, and things like that. So there are 9 parameters. I have a slide that lists all of them later on, so we can go over them. But these are climate characteristics. So the drivers are weather drivers, and the climate characteristics are just simply the average behavior of the climate in the past. So apparently, that also determines quite a bit of the relationship between the input and output behavior. And these are all coming out of the, and of course, these are all provided by, of course, NCAR CAMEL data set, but this in more general data sets that are becoming available now, people have constructed literally dozens and dozens of these characteristics. And I'll have something to say about that later on. But for now, these characteristics are coming out of the NCAR's CAMEL data set. And to a machine learning person, they could just be numbers, and then they won't really care about what they are. But Dave, thanks for asking, because somebody may wonder as to what this is. Do you think this provides sufficient information, or would you like to expand on it, perhaps?
Yeah, no, that's exactly what I needed to know. Thank you.
Oh, okay. All right. So coming back to this one, so in the gauge basin scenario, the big surprise to the hydrology committee was that yes, these machine learning models, just by combining data from multiple catchments, can do a much more dramatically better performance, provide dramatically better performance than individually calibrated physical model. That was a surprise. And again, the more recent sort of interesting observation that we just made was that I don't even need to know the characteristics. Still, I can build a machine learning model that can leverage the average behavior. And this talk is not about that, but I'm just mentioning that this was another very interesting piece that sort of happened in our book. Now, if you go to a situation in which you have ungauged scenario, that means you see the setting on the right side, which is you have 400 basins for which you have all of the data during the training years in terms of weather and the weather drivers and the stream flow. And then, but you do not know the characteristics. And if I don't know the characteristics, and if I'm asked to go to completely different basins, different catchments, then basically I'm out of luck. And again, in the case of a physical model, you could run your physical model with default parameters in this ungauged basin, and your performance may be bad, usually very bad, because if the test basins have basically you're making a guess as to what these parameter values would be. In the case of machine learning model, you are in a similar situation if you do not know the characteristics. So if you're ungauged basin, if you don't know the characteristics, then there's a question mark here. That means this is a hopeless situation. But if you know the characteristics, if you know those 27 characteristics that we just talked about on the previous slide, then it is possible to build a global machine learning model on the training basins, and then test it and run it on this ungauged basin, for which you do not have any stream flow data, but this using the characteristics of machine learning model would work. And again, this was also shown by this group at Google, Kretzer et al., that of course the performance becomes worse as you go from training to test. But even here, I think the biggest message there was that even in this situation of ungauged basin with known characteristics, they were able to get at least as good performance as as you would have gotten if you were able to calibrate individual physical models using the training years of data. So it was, again, a very important result. That is, the machine learning models are quite powerful. They can use the characteristics to learn a global model and use them to transfer it to ungauged basin scenario. Okay. Now, of course, things become really tough if the characters are unknown, which is the third column. You can't apply the Kretzer model at all. Or if the characteristics are uncertain, that means if the values of the characteristics are not as good as they should be, or they're only sparsely known. So if they're uncertain, I'm going to talk about it later again, but if what Kretzer et al. Showed was that if the values of these characters were corrupted by, let's say, half a standard deviation, then the performance dramatically reduces. And again, you will see that in one of the later slides. Okay? So now the third situation, which is of course of very interest also, that is you have you don't have an ungauged scenario, you have a limited gauging scenario. That is, you have a whole bunch of basins for which you have a lot of data, training data, but for the one that you're testing, you have small amount of data. And of course, if you have that situation, you could use a small amount of data for calibration of your physical model. And again, you can run into issues of equifinality, or you could, if the characteristics are still known, you could still use Kretzer et al. Model. But if you don't have the characteristics, this is where the inverse modeling becomes absolutely essential. That is, the question is here, I have small amount of calibration data. Could I use an inverse model which has been built, which has been trained using the basins for which I have a lot of observations, which is the training basins. And once I have a small amount of data, can I use them to jumpstart my inverse model and get these characteristics? So this talk is about how do you build this inverse model? Yes, go ahead.
Sorry, getting another question about gauged, ungauged, and limited gauged. The question is the only difference between how the trained test is partitioned, or is some training data missing from the ungauged?
Okay, so for the purpose of evaluation, I'm showing you the distribution between training and test. But in reality, you will have either gauged scenario in which I happen to have a bunch of basins for which I have a lot of training data, and I'm going into the future to do the testing. So in the scenario number one, I will have only 400 basins because I don't really care about the other 131. In the case of the very last row that I'm talking about, what you can assume is that I have a whole bunch of basins for which I have data, I have the input and output of a system during certain number of years, which is, and we'll use that for training. And then in reality, there'll be a new basin that shows up for which I only have a couple of years, a small number of data, small amount of data in the past, and I'm trying to make prediction into the future. So basically the distribution in training test that I've shown, I kept it so that people can understand the results that they'll be shown. But the gauge basin scenario simply means I have a past history and I'm looking into the future. Ungauge means I have a situation in which I don't have any past history for the basin of interest that I'm trying to make prediction on. But hopefully I have some other basins for which I have both all sorts of history, so I can build a model there. And in the limited gauge scenario, I'm looking at a basin for which I have very limited amount of data. I hope that's clear. Okay, so now I'm going to talk about this inverse modeling framework, machine learning based inverse modeling framework. And generally these models, of course, require a lot of data to train themselves. And there is a paradigm in machine learning, which is becoming very powerful. And it's called self-supervised learning. That means when you don't have data, of course, if you have a lot of training data, it's the best situation. But if you don't have a lot of training data, then can you somehow build a model that can supervise itself to a great extent? And of course, it probably won't be able to do everything by itself. But the question is, how far can you go without needing any training data sets? Now, the term self-supervised learning is a very recent term, but the underlying principles have been used in the machine learning community for almost 40 years. Back in the 1980s, when the neural networks became, which is the second generation network, people were already working on autoencoders. And autoencoders are some of the first examples of self-supervision. And basically what happens there is that you have created a methodology in which you create some sort of labels that are automatically created without needing any information that is very hard to get. But it helps you build representations, and those representations, when they're built, can help you solve your problem much more easily. So in the context of images, like image recognition, what people did was they sort of basically created labels automatically from the input data. And just to give you an example as to how you would do it, there are some examples like in painting. That is, I take this image you see on the top, on the right side, on the top right, you see the image of a bunch of people playing, and you sort of say, well, I'm going to hide a piece of this image in the training, in the input, and I'm going to force my neural network to reconstruct this image, but without having seen the middle part of it. And again, this white box in this image can be created randomly of different sizes in different places and for a whole bunch of images. And if it did that, then it would learn, assuming that you're giving it a whole bunch of images of sportsmen playing in a field, it will figure out that these are all people, and then people's arms and legs and bodies have certain shapes, and it'll learn to reconstruct. And there are many other formulations. For example, you can try to choose image from one color and try to reconstruct a different color. You can try to take an image and create jigsaw pieces of it and construct it. So the machine learning community has come up with all sorts of methods for self-supervision and creating better representation in the image setting. And of course, I'm not talking about images, so I'm going to talk about some idea that sort of were inspired by this, in the sense of methodology inspired by this. And here the idea is that I have a physical system which has input drivers, which is the weather drivers here, the output, which is the stream flow, and it's a time series of a bunch of variables X, and in this case, one variable Y. And I could feed it through an LSTM, and LSTM could be trained to build an embedding. It results in embedding at the end. And I can treat this embedding as a representation of the inherent characteristics of the system, which has input X and output Y. So the system, of course, I can build a LSTM like this, but if I don't give it any supervision, then it's going to be some embedding, which will be some sort of a random embedding. So I can create many different types of self-supervision. For example, I can sort of simply say that one way would be that I create these embeddings, and embeddings better be good enough to recreate these input weather drivers and streamflow. And of course, so I'm trying to learn a system in which I'm reconstructing the weather drivers and the streamflow, given these embeddings that is embedded by the LSTM. And in the process of minimizing the reconstruction loss, and again, it won't be very good reconstruction, but in the process of minimizing reconstruction loss, I may be able to build representations that are better quality. And the second thing I could do is, which is sort of coming very directly to hydrology, that I have these basins, and I'm taking these basins and I'm taking the weather driver from each year, and looking at the stream flow for each year. Now, for a given basin, generally the characteristics of the basin will not change over a period of time, not very much. And the characteristics of two different basins won't be as close to each other as they would be for a given basin for the same year. So basically the guidance here is the distance between embeddings of time series samples from the same entities should be smaller compared to samples from the different entities. So you take this information and you code that into the loss function of the machine learning framework, and then that becomes the second guidance. And again, these are not the only two different ways of doing it, but they're possible. And in cases in which you happen to know the physical characteristics of your basins during the training phase, and which may or may not be true, you can use another loss function, which is you can try to use this embeddings to build another regression framework to connect them to the actual characteristics. And if the characteristics don't match, then you basically have a loss function that helps you modify this embedding as well. So these are all and of course, I'm just listing you only three here. I'll show you results for only these three, but there are many, many other ways actually you can bring in the guidance in reconstruction of these embeddings. And once I have built these embeddings and done the reconstruction, then I'm going to show you these results for, again, for the CAMELS data set. And on the right side, you can see all of the characteristics listed. So the climate feature, you will see P mean, which is the precipitation mean. PET means is the evapotranspiration mean, aridity, seasonality, and so forth. So you can see they're all average weathers over a period of the data. So these are all the climate feature, average climate features. So some of the questions that we're going to try to answer here using this framework is, can I build a sufficiently good inverse model which would take the input weather drivers and output flows and recompute characteristics of the basin, and how well can it do it, right? And then of course the idea we are assuming here is that characteristics available for some basins which are going to be used for training, but for the others they're not available. So for the basins, training basins, the characteristics available, the input weather drivers are available, output stream flow is available. But when you go to the test basins, I only have the weather drivers and stream flow, but not the characteristics. Second question that we're going to sort of see is the model robust enough to correlate characteristics? That is, what if in the training set I gave you for many of these basins, many of these characteristics are corrupted. They're not the quite right characteristics. Or the characteristics may be available for some, but corrected for the others. So they're all, so basically characteristics available for some, but corrected for the others. So there you could have a situation like this. Or you could also have a situation in which characteristics available for some, but not available for the others. And then the third question we're going to see the answer to is, what if I do not know anything about the study characteristics? So you see these 27 characteristics behind this bubble. What if, as a machine learning person, nobody gave me those characteristics? Somebody just gave me only the input weather drivers and the output behavior of a basin, stream flow. And for a whole bunch of basins, could I reconstruct these characteristics, or could I reconstruct surrogates of these characteristics that are meaningful? And the third case is the one in which, if that works very well, it means that if you're missing some hydrological knowledge, could you reconstruct it? That is, if you're in a situation where you do not have the domain knowledge, could you reconstruct that knowledge? So that third one actually is very interesting by itself. So again, I'm going to remind you of this experimental setup, which we have seen before. Again, I'm building an inverse model. That is, during the training data, I'm using the X, the weather drivers, and Y, which is the stream flow, to feed into the inverse model. and construct the steady characteristics. And this is the first result I'm going to show you. That is, I'm giving you these 400 training basins. I'm showing you results on the training model built on the 400 training basins. The model, I showed you the caricature of that a little earlier. And once the model got built, I am testing it for the 131 basins in future year. That means there's nothing is there's the training and test years have very different time frame. And the question is for the test frames. Of course, we know the camel catchment characteristics from NCAR benchmark. So the X dimension is the what sort of camel has those values for the characteristics, and the Y dimension is the values that are reconstructed by this inverse model during the unseen basins, during the test basin. And you can see that many of them happen to be on the diagonal. And you can sort of say that the KGSSL knowledge-guided self-supervised learning framework is able to learn a function to impute characteristics or to reconstruct characteristics. And of the 27 of these characteristics, 20 of them have correlation of more than 80%. 14 of them have correlation greater than 0.9%. For example, some of these characteristics like soil, many like soil conductivity has a correlation of like 0.86. So you can sort of see that there is a reasonable reconstruction here. And for some characteristic reconstruction is actually poor. And it could be because perhaps those characteristics could be erroneous. They could have incorrect values or could have uncertain values, or maybe they don't play as much of a role in the relationship between input and output. There could be many, many different reasons for it. And again, we can speculate on these reasons. We can talk about the performance of this model on a much larger data set for which we have been working on right now on a global scale. It's 7 different regions of the world, and I may have something to show or talk about that. The second one is what if my training set has many of these characters corrupted? So what if I added 2 standard deviation noise, which is a pretty strong amount of noise, to half of the characteristic? That means I have this matrix of 531 by 27. In this case, I take this matrix and I just change half of these values by big number. And my model is going to be trained using corrupted characteristics in the training year, in the right half of the years, and the characters are going to be reconstructed during the unseen test years. And let's see what happens then. And you can sort of see that I'm just showing you illustration for elevation mean. You can see the 2 standard deviation sort of makes the characteristics quite a bit different from each other. And once you reconstruct them, they just sort of come right on the diagonal. And this is just one characteristics. You can sort of see the RMSE coming down for each of those characteristics from a very high value, like 2 standard deviation, as you're seeing here, to a much, much smaller number, as you see in the green values. So it sort of shows that representational learning framework is able to significantly reduce the error in the computed characteristic, which means if I was building this model, even a machine learning model, a forward model, and if I had to deal with errors in the characteristics, it's possible for me to make these corrections first and then build these errors. Now, the third question is, what if I knew nothing about the characteristics, which means of the 3 loss functions I talked about, I only happen to have the first 2, the L1 and L2, and L3 is not even there. That means I don't know any characteristics of any of these basins. What would this embeddings look like? And this was sort of this is an interesting question, because this means that what if I didn't even have some of those characters? What if some characters were missing? Would I be able to still make this machinery work? And what you're seeing here is the result of inverse modeling framework build, which is completely self-driven in the sense that all it takes is the input and output behavior of these basins, of the 400 basins, in certain number of years, or actually in this particular case, since this is unsupervised, so we use all basins because we use all the basins, build a model without looking at the characteristics, which is only the 2 loss functions. I'm only trying to reconstruct the weather and the stream flow. And I'm also trying to make sure the embeddings are different for each basin. And now if I look at, so each basin, each CAMELS basin, each CAMELS catchment has static characteristics which are known, 27 characteristics. And the left matrix that you're seeing here is the pairwise distance between each basin using the characteristics that are given in the CAMELS data set. We have some certain structure. Some of the basins are closer to each other, some of them are farther, and you see this the color bar is telling you what the structure is. On the right side, basically, we are constructing a similar matrix, except this time, rather than using the known characteristic, which we don't know, we're using the distance with respect to the embeddings. But all of these embeddings, they have 32 word vectors. So basically, using those vectors, we can compute the difference. And then it turns out that the relationship between these basins in terms of distance function, according to the learned embeddings, is actually very similar to the ones learned using known embeddings. So this gives us a sense that perhaps these embeddings have some physical meaning. And just to sort of see as to exactly how, do they have any connection to the known embedding, we actually created correlations of the embedding values along the 531 basin dimension and the static character and their known static characteristics. So you see on the Y dimension are the 27 characteristics, the climate characteristics, the soil characteristics, the geomorphology, so that you see them all on the left column. And on the Y dimension, on the Y dimension, and on the X dimension, you see the 32 dimensions that are learned by the machine learning model. And you can see that quite a few of these embeddings naturally have very high correlation with the known characteristics. Anytime you see a dark box, it's a very, very high correlation. And you can also see that many of these embeddings have high correlation with multiple of the characteristics, which many of them, of course, make sense. So, I mean, if you look at the actual value of these, if you spend some time looking at this picture and the corresponding numbers, it would sort of seem to make sense that it is what it is that they're getting here. So this gives us hope that even in situations where the inherent characteristics of the system are not known, this methodology may bring some light and may find some higher level relationships among these characteristics. Okay, my last sort of evaluation is in the context of that. What would happen if I built the inverse model? And in some cases, the inverse model, output of inverse model may be maybe what I'm interested in. That is, I'm just interested in the characteristic. But in some cases, I need those characteristics so I can put them back into a forward model, improve its forward modeling. So this is showing the context in which I would potentially use the inverse model like this to rebuild the characteristics and then use the characteristics then effectively to run the forward model. So here just for the illustration that this forward modeling, just for the illustration that the characteristics learned using inverse model are good enough. So we have sort of created this scenario in which I have again the 400 basins that are going to be used in the training setup, which means the right set of years would be used to build the inverse model. And when you come to the test model, if you're building a standard machine learning model, which was only doing forward modeling, using the known characteristics of the, and if you take the global model and bring it to the test basins, that model, as we said earlier, works very well as long as the characteristics of the test basins are known. But we're going to show that what if the characteristics are unknown or perhaps uncertain? What happens to the performance of the forward model and how much gain could we get potentially using this inverse modeling framework? So basically okay, so let me see. I think I have covered this part. Let me come back. Okay, so if you look at this picture here, this is a basin which is coming in from the test. The model has already been built on the training basin. We're looking at the test basin here in the lower 131. And one of the basin basically is showing the baseline prediction, which is the blue line, which is the streamflow prediction for 1 year. And the observations are shown in the dots. And then the baseline is showing that if you took the model, built on the training, and then you transferred it to the test basin with known characteristics, the blue line captures reasonably well the dots. But if the characteristics were corrupted, let's say by half a standard deviation, even by half a standard deviation, then the global model becomes really bad. It basically it gives you the performance in the green color. And again, this results like these were shown by Presser et al., which was sort of trying to show that you can build a model in the training basins and take it out. What they sort of reminded us is that if you know the characteristics well, you can really do a good job of using the machine learning model. Of course, if you don't know the characteristic well, then as this slide shows, it will be pretty poor. Okay? Now the question is, what if I reconstructed these characteristics using my inverse model? What would the performance be? And what this is what we're going to sort of show on this slide. And the upper part of the right inside of this slide is the one that you saw before. And the lower part of the slide is what you sort of see, that is, even if you had only 3 years of data in the testing period or from the training period, you can use that to reconstruct a model. You can reconstruct the characteristics, which are actually giving you almost the same performance as the blue line, and perhaps even better. And this is sort of giving you a more comprehensive picture. That is the baseline method. If you know the actual characteristics, you will get a mean C of 0.56. If you add half a standard deviation noise, the performance drops to 0.47. If you add 1 standard deviation noise, it becomes even worse. KGSSL model, which knows nothing about any characteristics, even using 1 year of data, can get you as much performance as the half a standard deviation of noise. And as you get more and more data, actually it can even outperform the case in which you know the characteristics. And again, I talked about this methodology for the hydrology, but we are applying this to many, many other contexts, including some of the work we're doing with USGS on modeling the lakes and the river systems, and some of the other work we are doing in the context of modeling the greenhouse gas emission from agriculture and several other contexts. With that, let me stop, and this is a list of my broader sort of team members and collaborators from around the country, and I am happy to take any questions at this time.
Thank you, Vipin. Do we have any questions? People can raise their hands, ideally, and then, or just unmute yourself. Question.
And I can then share my screen. So,
yeah, I wanted to ask about the embeddings versus the characteristics, right? So the embeddings, like, because you're actually reconstructing an actual value for each of those characteristics, but the embeddings are sort of how you get there, essentially. Like, because you were comparing then the embeddings to the characteristics. Can you sort of just explain the connection back to the final result?
So the characteristics are, and again, a hydrologist or a climate scientist like Dave Lawrence could tell you more. There are many, many different types of characteristics of a hydrological basin that may determine the relationship between input and output. CAMELS happens to have a couple of dozen of those characteristics, about 35 or 36, of which Presser et al. Happened to choose only 27 for the results, which is why we ended up using them. But there's a new data set called KARMA, which is being produced again by them, by the Google folks, on a global scale, which makes it easy for anybody anywhere in the world to take their streamflow data, and they have created weather data from, weather data is available globally anyway for large part of the world. And they have created something of the order of 70 or 80 different characteristics. That is, there are many, many different types of characteristics of an area which would determine the behavior between input and output. So what those characteristics are, as you think harder as a physical scientist, you can maybe make a longer and longer list. That's one part. Second thing is, for many of those characteristics, it's not clear whether you know their value or not. Just because I know that the soil porosity of a basin is important for determining the input-output behavior, but my basin has hundreds of squares of kilometers, and I don't know the porosity everywhere, and I don't know how to compute the average one, right? So, so what I'm trying to say is the number of characteristics is determined by what the scientist thinks is important, number one, or what they think can be computed, or what they know about. Maybe they just don't know about certain things that are important. Okay. Now, the good thing about machine learning is that this framework, which does not use the characteristic, the part that does not use the known characteristic, is that it says, I know the input and I know the output, and I am just trying to figure out what are the aspects of these relationships that are governed by some numbers. So it's creating actually a space, it's a basis function automatically. Now you would sort of say, this is a hopeless situation. How could you even do that? Which is why I showed you that matrix in which I sort of said, look, once I construct this basis function, does it have anything to do with reality? And you sort of say, indeed, it does, because it's very highly correlated with known characteristics. That means if some characteristics are really good, you can see them in action. So in some sense, one could say that if I have no understanding of a underlying physical scientific behavior of a system, I could still use this methodology to construct bits and pieces that may help me guide further. And again, I'll take an example. For the physical sciences, people have over the last decades and multiple decades have figured out what aspects of the physics sort of drive over climate system. But if I'm looking at the healthcare scenario, I don't know these basic equations. I only know the input-output behavior. If I am Amazon and trying to figure out who to sell, who to make a pitch to buy a product, I only know what they have been sort of buying over the last many years. So what I'm saying is that the key thing is there's a relationship between output and input that is determined by certain characteristics. And if I don't know anything about them, this methodology tries to find bits and pieces of that automatically. David, you have a comment question?
Yeah, can I just clarify? I guess, sorry, Dave, so understand what you just said. I understand a lot of that. But my question is, if the embeddings aren't related to the characteristics, then how do we get back to the characteristics that we know that you say are quite predictive? Like, is it just because the random combination of them that we don't quite understand is getting there? And how do we move forward and better connecting those embeddings to the physical properties?
Okay.
That was the question I was actually asking.
All right. Okay. So the first part of the answer is that even if I am unable to connect back to the characteristics, I can still do everything in the embedding space. Okay? That is, I can still calibrate these embeddings using small amount of data and go into the forward setting. So I don't really need, I can run my entire modeling enterprise without knowing these characteristics in certain context, right? That's one part, which is the I'm sort of making a statement that's the part that's the most interesting part of this entire paradigm. Okay? But in cases where you do want to reconstruct the characteristics, all you need to do is know some of them for some basis. And then you can use that to reconstruct. So for example, I didn't show the results. In all of these, I was talking about, I built the machine learning model on 400 of these and tested on 131. So in one of the experiments, we sort of said, well, what if I knew the characteristics only of 100 of these basins? Okay? Or what if I knew only 10% of the characteristics, others were missing? Could I still learn the mapping between embeddings and characteristics? And actually you can. So what I'm saying is that learning the embeddings is the hard part, for which of course you need a lot of basins and a lot of years. But the relationship between embedding and the actual characteristics, as long as you knew some of them, as long as you knew some of them correctly, others could be wrong, others could be missing, they could be wrong. The machinery still figures out what the right mapping is. So if you need the characteristics, this methodology is helpful. But the beauty is that you can do pretty much everything you want to do without knowing these characteristics. In many cases, you can do even better because you know characteristics because you must have done a lot of work. But for this embeddings, all you need is the data, and then you reconstruct them from scratch just by training this machine learning model. David, you had some comments or?
Yeah, I guess my question is, relates a little bit to Galen's, I think, although having a hard time following all this, but I'm a little bit confused about why you're considering these climate variables as a characteristic, right? Because to me, you might imagine that the thing you're really trying to do is, treat all the unobservable quantities. Like, so the climate's an observable quantity. And even some of the other quantities that were in some of the other characteristics like forest cover or leaf area index, those are observable quantities. But the unobservable quantities is, everything that's happening in the soil, geomorphology that is, largely unobservable. And so I'm not sure exactly what the question is, but, have you, what would happen if you just removed the characteristics that were observable characteristics and just used the unobservable characteristics as an example? And would that be practical?
And we tried all of that. Right? I mean, this didn't show it. And actually, when we moved from CAMELS to Karma, which has about 60 plus characteristics, I think those guys built it, for about a couple of thousand basins, all of the CAMELS data set is there, most of it. Almost equal number of basins from UK, a couple of hundred basins from Australia, many hundred basins from Canada, from Europe, from Chile, from Brazil. So there's 7 different regions. And we've applied this methodology to every one of them. And it turns out, and again, and David, as you said, the reconstructing climate characteristics is not very exciting because, you can easily, number one, you can just the averages in any case. But the exciting part is that a lot of these soil characteristics, like soil porosity, you can reconstruct them to the 0.98 correlation for the US. And if you look at all the 7 regions, each one of them separately, every one of them had the soil porosity reconstructed with a correlation of more than 0.9, and most of them had actually more than 0.95 or better. So what I'm saying is that these are the characteristics that are completely hidden. They are not something that you're observing from the satellite, or at least the machine has no way of knowing it. And many of the characteristics are actually very well constructed using this. And your other question is, if you knew some of them, would it help you know the other ones better? Of course, in general, of course, if you knew some of them, you could learn the other one better. But the data of the 10 years, 20 years data was rich enough that it could reconstruct them pretty well, even without having access to any of the other ones. So this was a surprise. And again, these are the beginning phases of research. There are many more questions one can ask here, right? In the sense that the first part is, well, can you build a model like this? The second part is how many different scenarios this model can be tested and made to work. And which is why, for me, being able to go from the CAMELS alone to the 7 different regions of the world was extremely important, right? To show that the machinery as it is out of the box is working beautifully in every one of those regions. And for some reason, the numbers were even better. Perhaps these Google guys did a harder job in collecting the input-output data and for a little bit longer duration. And I have some comments to make afterward, but I see another question here.
Great, thank you. I have to run, unfortunately, so thank you, Vipin.
Yeah, so Rajat Chowdhury is asking, how would these models account for changes to basins, such as development of controlling structures, regulated structures? And if you had, can you expand the methodology if you add things, add more data in addition to stream flow, such as soil moisture, groundwater, and evapotranspiration?
Okay. So, all right. So I think the first part is, what if you have controlling structures? So, for example, I'm assuming you're looking at what if there is a dam which is being managed, and again, we have a separate stream of work on that direction, which looks at that directly. I mean, in the sense that there are many papers from our group and extended group directly addressing that piece of work. But in this inverse modeling framework for now, this human intervention has been excluded, in the sense that if the human intervention is something a little bit harder for us to figure out. But even in this case, I can imagine that if you gave me a whole bunch of data for stream flow from multiple sets of basins, some were governed by human behavior versus the other. One could ask the question, could you figure out just this bit, whether it's human governed, human directed basin versus not? And whether we can do it or not, it's still a question, but methodology may be useful there. And again, as I said, we have not tested it. But let me look at the other question here, which maybe I may be able to give you a little bit more answer. If additional outputs such as soil moisture, groundwater, evapotranspiration is considered along the stream flow, is it possible to expand this methodology? Okay, this is a very interesting question. And actually, this is the part that we are studying in the context of greenhouse gas emissions. So the idea here is that you have agriculture, you're growing some plants, you're growing some food, it's driven by the weather. You're looking for the yield and looking for the greenhouse gas emission from the process of growing crops. But then you also happen to have access to other data sets from the satellite, like the soil, like the evapotranspiration. And the question is, how do you leverage all of that together to build better models of this greenhouse gas emission? And this work is not published yet, but it's being submitted for a manuscript, and it's joint work with some of my colleagues here at the university. And it's just showing dramatically better results than what you could possibly get using pure physical models, which are hopeless for calibration, because there's so many parameters, one is not able to calibrate. Whereas this methodology, inverse modeling methodology, modified along the lines this question is suggesting, is able to provide a much better solution than pure machine learning or pure physics models. And that may be subject of a talk in the future.
Okay, Jianying has his head up, so could you unmute and ask your question?
Okay, yes. So thank you so much for this exciting talk. I find it to be very inspiring. So I have maybe two related questions. So one is that when we are attempting to learn the static variables or the embedding of the system governing the hydrology in a basin, maybe some of these like inner processes are governed by like processes with long residence time. So let's say there are some fast processes in hydrology, but there are also slower processes, such as those involving vegetation, root uptakes. So when we are setting up an LSTM or a dynamical system like that, I will be curious to know, like, how do you set up the length of the sequence in order to reliably retrieve these parameters, given that these processes may be governed by both fast and slow processes? And another related question is that because in many cases we do not know the initial state when we are training, let's say using segments of our training sample, and maybe the inversion algorithm is often sensitive to these unknown initial conditions. So how do you make sure that your model like either sufficiently reach an equilibrium or like it spins up sufficiently so that these parameters can be reliably retrieved?
Two excellent questions. So let me answer the second one first. And the second one, actually, the model basically takes only 1 year of window. So basically, you can take in the test set any 12-month window. You can sort of slide it in any direction. Okay? And the model will take for the 12-month window starting on any month of the year and reconstruct the embeddings once it is trained, right? And for the training, it's the same thing. That is, windows are created and then put into the machinery that I showed you, right? So the answer to your second question is actually very simple. That the 1 year window is good enough, and there's nothing more need to be done. Your first question actually is very, very interesting. It's interesting from the following perspective. If you look at the hydrology literature, and not just hydrology, but much of the physical science literature, you literally find hundreds and hundreds of papers that are using machine learning, specifically LSTM, to serve as a surrogate for the hydrological model. Okay? And paper after paper sort of show that pretty decent performance. And these models are being used, LSTM models are being used without regard to the context that you provided. That is, you have all of these different variables. They're all changing at different scales. Soil changes much more slowly than evapotranspiration or precipitation or the weather. But if you look at the LSTM architecture, they'll be feeding all of these variables at the same scale. That is, they're just coming into the input and creating a state and going outward. And I should say they're lucky that they're able to get quite far with this. But again, one of the recent papers from our group, again, just getting ready for publication, addresses this question head on. That is, if you knew that these variables were happening at different scales, could you use this information more effectively. And then it turns out that there are much smarter way of building the machine learning models that are faster in terms of requiring less computing time, or even better quality results, providing better quality results if you happen to pay attention to the issues that you just talked about. As I said, this is exactly the topic of our paper that we're sort of sending out right now. But excellent question, and it's amazing that all of these people in the hydrology community who are just learning these models, they're not at least asking this question as to how is it that this LSTM that was invented for the sole purpose of translating text from one language to the other is being used mindlessly in this context? And shouldn't we be doing some innovations here that are very specific to the physical sciences?
Okay, last question from Harry Sheep again, asking the question, what are embeddings? That'll be, I think, the last question. Okay, so you can for this question, you can assume embedding to be just a basis function or just a collection of words. Basically, they're just in this particular case, there are 32 words which are initialized to 0 or to random values to begin with. And as you run through the machinery, these numbers will end up being something different. The words would be something different. And together they represent some aspect of some hidden characteristics of the system. And you would sort of, your inclination would be that, how do I know this characteristics mean anything? And which is why I showed you that slide. That is, if I took those characteristics and showed the correlation of these characteristics with the known characteristics, you could sort of see that actually they're learning something very, very close to what people think, what hydrologists think is important. And in areas where you know nothing, this characteristics would be, of course, something, and then all they're helping you is determine the behavior between the input and output, and then you'll have to recreate what they mean from scratch. Okay, great. Well, that I think we'll end it there, and we'll thank Professor Kumar again for a very interesting talk, and we will hope to see everyone either online or in person in 2 weeks for the next LEAP lecture in climate data science. So great, thank you so much.